Good morning, everyone. This is Xin Luo from the University of Michigan. I'm a PhD student. My advisor is Professor Yogesh Gianchandani. Today, I'm going to present our recent work on a miniaturized high-voltage generator for the applications in a microsensing system. I have divided my presentation into 5 parts. They are background, device design, fabrication, experimental results, and a summary. Let's get started. As we know, for a self-sustained microsystem, harvest environmental energy instead of using batteries to power MEMS devices is of great interest. So, substantial efforts have been made to build energy harvester based on piezoelectric materials, such as PZT. Those work directed at optimization for conversion efficiency and low output voltage. However, a number of sensing principles require high voltage supply, such as microdischarge-based sensing. The typical required voltage is over 500 volts. Thus, for those devices, miniaturized high voltage generator is highly desired. In order to meet the high voltage requirement, we target at a high voltage generator for the range of 100 to 1000 volts and to be used in the microdischarge-based sensing. Let's move to our device concept and design. The high voltage generator utilizes a single PZT disc of 5 mm in diameter and 740 microns in thickness. It's working in D33 mode. In another word, the PZT disc will generate charges and build voltage between two surfaces along the direction 3 in response to the mechanical load in the same direction. For those of you who may not familiar with the transducing principle, it is due to the piezoelectric effect. Theoretically, the built electrical potential is uniformly distributed on the same PZT surface, which could be regarded as a parallel capacitor. However, the PZT itself is not conductive. For this reason, when we deposit electrode pairs on both PZT surfaces, they will form individual capacitors with smaller capacitance. So the idea here is, if we series connect those individual capacitors, the output voltage will increase. So like we connect several batteries in series to get a high voltage. In current design, we use 3 electrode pairs and connect them by a flexible Kapton cable as shown in this figure. In theory, voltage could be n times large if we use n pairs. However, the fringe capacitance will diminish the performance. To validate this idea, we did a simulation using finite element method on the voltage generation in response to mechanical pressure. For the simulation result, the electrical potential is unevenly distributed on the PZT surface. When we alternately connect those electrode pairs, as a result, the maximum voltage is much higher than that without the electrode connection. Next, let's look at the fabrication and assemble part. The fabrication begins with a 1 mm thick, 5 mm in diameter PZT disc, and then we lap it down to 740 microns to reduce the influence of the fringe capacitance. Following this, we pattern the PZT disc on both sides with chrome gold electrodes. Then we use a 75 micron thick flexible Kapton cable to wrap around the PZT disc to make electrical connection in series. Finally, the sandwich structure is formed using both glue and conductive epoxy for different bonding parts. The assembled device is shown in the bottom photo compared with the US panel. Next, I'm going to talk about the experiments. As I discussed before, the device converts mechanical stress into electrical output according to the piezoelectric effect. However, due to the charge leakage of the PZT material, we could not get a constant electrical output with static mechanical input. So in the experiment, we applied the transient mechanical load by dropping a small stainless steel ball with a diameter of 6.8 millimeter. And this transient mechanical load is measured by a load cell where the device is attached. The electrical signal is measured through a resistive divider to minimize the influence of the capacitance noise introduced by the oscilloscope. The transient energy may be shock related or acoustic. That remains to be determined. The possible applications include harvesting energy in underground or underwater environments. This slide shows the important experimental results. The plot indicates the high voltage generator produce peak high voltage from 100 volts to 900 volts for the mechanical range from 1 to 5 megapascal, which is shown in this blue data curve. As a comparison, we also tested another device only has one electrode pairs. It's shown as the red curve. As you can see, the plot speaks for itself. The output voltage is greatly increased using this series connect method under the same mechanical input condition. Another finding is that the nonlinear piezoelectrical effect in transient mode is found. Although this nonlinearity has been studied before for static mode, nonlinear property in transient mode has not been previously reported. Classic model of the piezoelectric effect is a linear relation as shown in the upper right equation. Nonlinear effect has been investigated in static mode, and it turned out the piezoelectric coefficient D33 is a linear function of the applied stress. And this nonlinearity is also obtained in this transient mode experiment. If you look at the bottom left plot, you will find the blue data points, which are the piezoelectric coefficient, is a linear function of the applied stress. Now we have experimentally shown the capability of high voltage generation. In a further step, we demonstrate the application of the generated pulsed high voltage on a microdischarge-based chemical sensor. First, let me explain how the microdischarge-based chemical sensor works. The core component of the sensor chip is a 1 by 1 centimeter square glass chip with patent electrodes. There is a 75 micron gap between the anode and cathode. When the applied voltage across the anode and cathode is high enough and beyond the breakdown voltage, which is normally around 1 kilovolts, then the microdischarge will happen. The optical emission light is then captured through an optical fiber and analyzed by the spectrometer. The chemical characteristics are unique for specific elements and chemical bonds, which will reflect from the spectra. We have published this sensing concept before in the IEEE Sensor Journal. In this demonstration experiment, we use our high voltage generator to provide high voltage power to initiate the microdischarge. The experimental results are promising. As we can see from the photo of the sensing electrode, the microdischarge are successfully initiated using this high voltage generator. If you look at the transient response pulse, the peak voltage of across the ballast resistor is over 1 kilovolt and is built within a few nanoseconds. So to sum up, in this work, a pulsed high voltage generator is designed, modeled, fabricated, and tested. The key idea is series connecting electrode pairs on a single PZT element through a flexible Kapton cable to achieve higher voltage output. From the experiment, the device generates a peak high voltage from 100 volts to 900 volts in response to the mechanical load from 1 to 5 megapascal. From the comparison with the one electrode pair, we conclude that this method indeed increases the voltage output by a factor roughly equals to the number of electrode pairs. And the nonlinearity has also been found in this experiment. Last, we successfully demonstrated its application on a microdischarge-based chemical vapor sensor. Microdischarges are initiated and the peak voltage is over 1 kilovolts. That's all. Thank you for listening.